Yeah, hello, I'm Cheuk. And so I always said, like at the beginning of my talk, this is the most important slides ever because there's a link there. Can you see that? And that with this link, you can get everything in the slide deck. So please, maybe if you want to take a picture, like feel free to do so. Also, there's like my contact information there. I'm on the Twitter and also same handle for Mastodon if you prefer that, and also other social media and stuff. So yeah, you can find me there. So I'm Cheuk, yeah, again, sorry, repeating myself. I work for Anaconda and I love open source projects. These are a few that I've been involved in the past. I've also contributed to a few more. And I organize events, so I will tell you more about like which conference you should go next. So talk to me if you want, if you enjoy your time here and want to go to more conference, you can ask me. So, who have seen the Memray era? Yes. So I think that because like we are doing data science work, a lot of times when we have lots of data, this is very common, Memray era, which means that you're running out of RAM, and it's not a good thing. Some people may solve the problem by spinning up a bigger cluster, but that would be expensive very quickly, so it's not the best solution. So we have to do something called memory profiling to help ourselves to get out of this trouble of running out of memory. But what is memory profiling? So it's a very tricky question if you haven't heard about the term before. So let's just make sure everybody's on the same page, because like you may have different background, you may be like data scientists and don't care about this too much in the past. I'm going to tell you that you should maybe be more aware today. And in software engineering, profiling means that you're investigating your code, the software's behavior. So when it's being executed, you kind of want to see what's going on. So that is called the dynamic analysis. So of course, the contrast will be static analysis. So static analysis is basically there is a other tool or software just scanning your code as if it's a text file, so it doesn't really run your code and check what's going on in your code. Maybe like investigating something called like AST or something to see like how your code is structured. So that's static. But dynamic is actually what's going on in runtime. So when you run your code and there's a tool to see what's going on when the code is running, that's the dynamic analysis. And so any tool that actually do this kind of profiling dynamically is called a profiler. So of course, we are talking about memory profiling here, as the name suggested, is a profiling, plus is for memory, for the how much memory your computer is using. So lots of these kind of time, we are talking about the memory allocation of your software. So for I'll go deeper a little bit in the next slide, but lots of times, when your computer is running the code, it's not just like, have a box of memory and trying to view them. Your computer is like doing better than that. They can like sometimes swap the memory and stuff, so you can actually run programs that require bigger memory than what you actually have. So those kind of problem of how to allocate the memory, how to use it efficiently, those are actually something that you have, you may need to, so your computer is supposed to be like handling it very well, but you may also want to keep an eye on it. So that's why we do the profiling of it. And also the garbage collection, a lot of times, you have heard this term before, garbage collection, memory leak, and all this is because sometimes for some memory allocation, the computer program is supposed to be like keeping track of these things that occupy this memory. Are they still in use? Are they still useful? Sometimes if it is not useful and we lost the reference, then those are actually lost memory. So garbage collection is basically avoiding that, and if something is not needed, free up those memories so you can other process can use the memory more efficiently. So also, it's, like I said, it's a dynamic analysis. So the memory profiling is basically happening when you run the code. So when you run the code over the time, you see what's going on. Sometimes, some tool will give you a graph of see like how the memory, how much being used at a certain point. So, but why do we want a memory profiler? I keep saying like, oh, we should maybe start thinking about it if you haven't think about it before. If you are a data scientist or you work with data, and I just want to see what this data story is going to tell me and all stuff. But actually, this can also affect your work because we don't want memory error. And who have this nightmare of you have a Jupyter notebook, you have run all the cells, and you your thought is actually thinking about how to manipulate this data and stuff, and then you get this memory error. You have to run the notebook again. It's very annoying. So, so that's why we need a profiler. We need to try to see whether there's some part of your code is using a lot of memory unnecessarily. So that's why we want to profile it. And data science work especially involves a lot of data. It could get big very quickly, right? Load in a huge CSV file. It exploded at it. Because we had a conversation, I have a conversation with other speaker earlier, and we talk about loading a huge CSV file. It got converted into another file format that really is really huge. It's like putting some popcorn kernel in a pot and then you're cooking it and then it just exploded and it just filled up the whole pan. It's like that. So we have to keep an eye on it. And the other problem is that because Python apps are not very good at memory allocation. Why I say that is because Python has its own mechanism to how to handle some memory allocation. For example, for small object, I will touch on that a little bit in the next slide. And so we don't want to, again, we want to avoid a memory error, or even something like sometimes it's worse when there's no memory error and your program is just hanging there forever and ever and ever and ever. Sometimes you wait because, maybe it takes a bit of time because it's huge, but sometimes it's just waste of your working time. You have been waiting for 15 minutes, 30 minutes, and this is time you could do more productive work and you're just waiting there, so it's wasted time. So we want to know what's going on. We want to really be more smart of how we run that program. So different memories. So again, this is for people who may not be very aware of the topic before. I just want to make sure everybody is on the same page. We have something called heap memory and stack memory. So, what are these? It sounds cool. So heap, a lot of time heap memory, you just call it heap. It will be stored in the heap or something like that. It just means that it's basically a space that is you can put things anywhere. It's like a room. You can put a luggage. You fill the luggage in the room, but you're not organized like me. I'm not an organized person. I just put it there, so you don't have to be arranging them in order or anything. So they can be anywhere. But the thing is, because it's everywhere, you don't want to lose it, and that's why you need a reference to it. You have to mark down where you put it, right? So that's basically the heap memory. It's usually for global variables because global variable is accessible at any point of your program. The other thing is called stack. So stack is basically used for local variable. A lot of times when we finish running a function, when you return, the local variable is not available anymore because they are stored in order. So when you are done with that, and then we can erase them in order. So they are no longer needed because the function got returned and then it's gone. So that's why that thing for stack memory we don't need we don't need reference to it, and then it can just be removed when we execute the program. When it's no longer needed, it will be gone. So usually when we talk about the problem of memory leak and garbage collection is happening in the heap because we lost the reference. Then another term that you see a lot is the residence and virtual memory. So resident memory is the resident set is actually how much RAM your computer actually has. So when you buy a computer, you check the tech spec and all this so it will show you how much RAM you have. That's actually the resident set. You can kind of guess how much you can use by looking. Of course, two computer, one is full. One is 250, the other is let's say smaller, then of course the bigger one you can have more memory, but it doesn't mean that you can only run that much. For example, 2 gigabyte and 4 gigabyte. Of course, I can have 4 gigabyte. Can it hold double the memory? Yes, but you can also maybe run a program that requires 4 gigabyte in a 2 gigabyte resident set because your OS will swap the memory. So when it's not used, it will go swap out. So those, like for example, the program that actually, for example, totally need 4 gigabytes. So that is the virtual memory there that we need. So virtually, so ideally, or like from the program's perspective, it needs 4 gigabytes, but you can run it in a 2 gigabyte resident set because Ting got swapped. So something like that. Don't mix the two up because it could be very confusing. So, why I can run like it's like magic, right? It's like, extra RAM coming out of nowhere, but it's not. It just got swapped. So that's how it works. And the tricky bit is different operation system will have a different mechanism of doing that. So that's why profiler, it could be very tricky to create a profiler that works on all the machines. So for example, Memray, which is the tool that we'll talk about, obviously, doesn't support Windows because someone needs to develop another mechanism for Windows. And right now the team in Bloomberg is, they don't have use case for Windows or this. That's why nobody is maintaining and creating it. So, but Python, Python works on all the different things, right? So Python got its own way of handling the memory, especially the small memory. So Python will keep a heap, private heap for itself. So that's why it's not the most efficient thing in the world because you just hold it, whether you use it or not, Python claims it. And Python will have its own memory manager. And it's kind of communicating with your operation system manager. So they work together. And in Python, there's like this thing you may have heard about it before, PyMail log, or sometimes you see it in the forum, people discussing about things for the PyMail log. So what are they? They are the Python memory manager, one of them. There are multiple ones, but the PyMail log is the one that handles all the small objects. So it will talk with another manager that is like, the name is super weird because it's in the C API there, so it's like very deep in what Python, like low-level thing, and it will talk with your OS manager. So they're all communicating with each other. That's good. So for different object types, they would have different sizes for them. So it's kind of, I would always think that it's kind of like a room, and then you have all these like boxes that you have to fill inside a room, and they are all in sizes like multiple of 8. 8, 16, and then you get up to 512. So anything bigger than 512, we won't use the PyMail log. It will be using the deeper like C API to handle all of these things. So the reason why it's doing it is because like in Python, there's a lot of like small objects, and then like integer is an object in Python, right? So everything is an object, and they are all small. So this is like efficient in a sense that it's easy to implement and also like kind of easy to maintain. So that's how it does. Also, like you'll see all these like terms of like arena, so it's just kind of like different sections in the room. That's how you have the heap, and then you have different arenas, and then you fill the boxes within it. So that's basically how Python works in a very oversimplified version. So. But then, that is all this basic background information. It's good to know about it, but we are not actually writing C Python, so most of the time we don't care too much about it. What we care about is what our code, right? We want to profile our code. So I found a tool, Memray, that is actually works on Jupyter Notebook. So first of all, Memray is designed for Python, so it kind of understands all this mechanism that is specific to Python, so that's why it works better on the Python code. The second thing is that it now has a Jupyter extension, so we can run it on Jupyter Notebook, which is super convenient if your work involves Jupyter Notebook. Yeah, but there's no Windows support, so I can't really help you if you're using Windows. So, right, so now I want to do a small demo. So we have around 10 to 15 minutes, so let's have a look. So this is, I hope it's big enough. If not, I can zoom in. Okay. I hope it's big enough for the people at the back of the room. And this is just a demonstration. That's how you can use Memray on the Jupyter Notebook. And so it's like all of these are percent magic, so they are just extension that was written that you can load in on your notebook. So of course you have to have Memray installed in your environment, but once you have it, you can load the extension by the percent magic. And this is an example actually I copied from the documentation. So it's, you know, if you want to see it, you can go to the documentation. Nope. Wow, it's very big, so it just jump. But anyway, like I run it, the cell with the percentage magic. So it's the frame graph that it's going to create. So the frame graph is basically an analysis that is visualized. So you can look at what's going on. There are also other options you can add to this like line of code there. You can add other options, for example, I'm using parallel and things like that. But check the documentation for all this detail. So this is the very simplest case of a code. This is in the cell, right? And then we are profiling all the code in this cell. And so this is a bit silly, you know, print a bunch of A's, and then, you know, in the list as well. So, but this is what you will see when you profile your code. You will have a frame graph that is shown to you. So this is a very simple frame graph. Okay, but I can see a bunch of boxes, but what do they mean? So let's have a look at what do they mean. So as you can see, this is a top-down view. So you can see like whenever some function is calling another function, you would just go down a level. So for example, this one is called by, so it's like A, and A is calling B, so that's why I go down this level, and then B is calling a list of C and D, and then this is C and this is D. Okay. You can also see some information in this like black box that pops up, but right now it's not easy to see because it's got also mean. So yeah, so this is if. So okay, now how to interpret this graph. So personally, I like inverting it because it's easier to explain. So lots of times when we look at them, we would talk about this length, so how wide this box is. So to describe it, I would say that like look at the roof of this. So for example, this one, it got a, you know, there's nothing on top of it, so it got a roof. So how wide of this roof is actually how much memory you use. But if you go down one level, which is like the parents of it, you can see that, oh, actually the width is double the size of these two child, right? So it is using, so the memory that this parent is using is double of this is using, but half of it is because it's calling this function. So that's why if you only call two functions, C and D, and then because it's like at, you know, the same time, so you can see like it's using these two, because it's constructing a list that is like the two of them together, so it's using the double the size. So this is oversimplified. Let's look at something more complicated and interesting. So let's run this one, and we have another frame graph. This one, so there's a few things to notice here because this one is not like, you know, same size. So let's invert it to look at the roof. So the roof here is more complicated because there are, of course, this is like the youngest, I mean like the last generation of cores. They have the roof, of course. But if you look at this one, this is a more complicated function. It's calling a few other functions. So it's calling E, calling F, and then it's doing something itself. So you can see that this block has a little bit of roof, because normally when I talk about, for example, this one, right? This one doesn't have a roof because it got two boxes on top of it. It only got the width, but it doesn't have the roof. It's because all the memory that it used is actually from the child, so it doesn't do anything itself. So, but this one, it has two boxes on top of it, but it's also got a roof. So it actually also have this bit that actually use memory within it. It's not, there's no other children functions to be responsible for that, so that's what it means. So a lot of times when we want to optimize the code, we look at the roof, look at where we can actually, you know, kind of trim down, or maybe that's not efficient and all these things. So roof are quite an important concept to have when we look at the frame graph. So there are other things as well. For example, you see there's a function called missing, and it's actually missing here. If you look at all these boxes, you won't find missing because is missing. But why is it missing? Is it because when C is calling missing, and because it doesn't really do anything except that it's like return a bunch of A, but then it's not used anymore. It got free up. The memory got free up when we return the function. It's already gone, so it's free because this missing is just a local, bunch of A's that's used locally, and when we return, it got released. So that's why it is not contributing to the whole grand scheme of things because it got released already, so it's missing. So it's not really something that holds up your memory by the time you return the function. So that's why it's not showing in the frame graph. So that's the basic of frame graphs. So I hope now everybody understands. So let's look at something that's more real, it's more like data science things, right? So let's look at how it looks like, especially pandas. We all have pandas. So let's do the same thing. We load in the extension. We will import pandas, and we would load in the CSV. We'll have a look at CSV. Oh, beautiful. Okay. So these are actually the ice cream reviews. So I love ice cream, by the way. And these are actually the product information. So we also have that. And I want to do some statistical analysis of it. I'll oversimplify again. So what I am doing here is to do some first of all, I want to get like a yearly score, like how each ice cream is doing yearly. So that's why I have to do some aggregation, group by of it, and then I aggregate it. So there are actually two ways of doing it, right? Because date is actually a string here. If you, I think I've linked to the repo that got all these things. So if you want to play around yourself, you will find that date is actually a string. So what you can do is to just quickly grab the first 4 characters of the string, right? That's the year, and then you can just use it to group by. That's the year. Or you can do it properly, convert it into a datetime format, and then you can take the year of it, and then you can group by. So that's 2 ways of handling it. I want to compare them. So I would have these 2 written as a function, and then I would use the frame graph to see their yearly performance. So I have another function that is like handling the rest of the computation. So the only distinction between these 2 is like how I'm using, how I'm getting the year aggregation. So let's have a look. Oops, I forgot to run this. Yes. Okay. So now we have a frame graph. Whoa, this is scary, right? Let me zoom out a little bit because it's too scary. Okay, so wow, so complicated. Wow. We are using pandas, and panda is complicated. So yeah, there are lots of boxes. It's not as simple as that, and lots of these are actually pandas internal. And it's using 1.4 gigabyte of memory, and I don't know what this is, But don't worry, you can always trace back to this one, which we know what it is, right? We've written it ourselves. So let's generate the other one so we can compare the 2. So that's here. Okay, so you see that the frame graph is actually different. And you can see that this is calling the second version, which is good. So we can compare the 2. Actually, the 2, you can see the shape are different. It could be because these boxes are swapped, but if you really inspect it, it's actually totally different because I'm doing different operations with 2, right? One is just getting the first, especially this bit that is doing the apply, because one is just getting the 4 character, one is converting them, so they're different. And so now it's quite difficult to compare because it's 2 graph. You can look at how many gigabyte of memory you're using, but not gigabyte, just megabyte of memory that you're using. But now since in the Jupyter Notebook, it's quite funky and it doesn't really show. Another trick when you are using Memray is that it will generate an HTML file for you, so you can find it here. Of course, you have to decipher which graph is which. So, for example, this one, not this one, sorry. This one I'm looking at is, so this is the first, this is the first one here, that it says that it generates this one under 19, so underscore 19, which is this one. So this is the first one. So we can open it in an HTML file, and it's actually have better view there. It's using 5.4 megabyte of memory for the first one. So how about the second one? Let's have a look. Second one. I need to get the code here it is, like this one, FBS. So let me find that as well. FBS. Oh, this one. Oops. I hope they're ordering like from the oldest to recent, but it's fine. So, oh, this one's also I can see it. So it's using. Why is it not showing? Yeah, it's a bit weird. Can I roll it? No. Maybe I invert it. So it's very naughty here. Yeah, sometimes it's okay. Now it's showing that it's using 5.5. So there isn't much difference. So remember, this one is 5.4. So 5.4 versus 5.5. So the two is not really different. But it's just showcasing a process that you could do to maybe if you have two ways of doing the same thing, you want to compare the performance, you can kind of do this to see which one uses less memory. Of course, again, this is an oversimplified example. You may be handling something bigger or more complex, but that's the way that you could do. So that's the end of the demo. And yeah, so Memray is a tool that you can use with Jupyter Notebook. I kind of forget the slides. This is the last slide. It's about, again, EuroPython. I think I have talked about EuroPython a lot as well. You know, if you're interested to go, talk to me. If you want to know more about, you know, what's happening in EuroPython, what do you have except just talks. There's a lot of activity you can do at EuroPython. Talk to me about it, and I will tell you more. So that's it for my talk, and it's Q&A time. Thank you. Any questions?
Thank you very much for your talk. I have a couple of quick questions. One is, I see you're using the classic notebook. Does the extension already work on Jupyter Lab? Not necessarily like Jupyter Lab 4.0 from 3 days ago, but Jupyter Lab in general. And the other question is, like, say I have two different ways of doing the same thing, and I want to visually compare which one is better in terms of memory usage. How would we do that?
Yeah, that's a very good question. So first of all, I haven't really like physically checked myself, but I bet it works on Jupyter Lab because it's just my preference to use Jupyter Notebook. That's why I'm using it. And also in the newer version of Jupyter Notebook, it's actually using the backend is using Jupyter Lab. So if it doesn't work in a newer notebook, if it doesn't work on Lab, then it will probably doesn't work on a newer notebook, which is not a good thing. So it will get support very, very soon. The other thing about like if you want to visually compare them, unfortunately there's not a single graph you can generate right now from Memray. So I think you have to either do the dancing I do, or you have to maybe generate another. You can log all of this, like check the documentation. You can log all of this, and then maybe you can do some analysis yourself because we are all data scientists. There's another question. Oh, wait, out of time. Okay, so let's talk outside if you want to ask more questions. Okay.